These are the acronyms we'll use. TOPS is the number of pair operations we'll do. GTDR is a type of DRAM. MAC is multiply, add, actually add what is not, multiply, accumulate. And SISC is complex instruction set computer. So first of all, why worry about TPU? So, you know, I'm sure you must have heard of AlphaGo. If you have not heard, please go through it on maybe some Wikipedia somewhere. So, you know, previously when Google designed it, they were running it on GPUs and it was taking huge amount of power. So then they started then they designed their own TPU. Okay, Google is not a hardware design company, but they designed their own TPU, so which reduced the power consumption drastically. And some of the further ones they just take for TPUs. So here you can see compared to 40,000 watts, so much power savings have been achieved. So that should motivate you. Yes, I should study about TPU. Okay, now let me tell you the big picture. So what is the big level difference between CPU, GPU, TPU? So in CPU, we have this hardware managed caches. Okay, L1 cache, L2 cache, implicitly managed here, which is same is also called hardware managed. Okay. Now in GPU, we have shared memory, which is explicitly managed or software managed, and we have L1 cache, and L2 cache, which are hardware managed. So GPU has both hardware managed caches and software managed cache. Okay. Now TPU and all the other accelerators we will see, I mean almost all the accelerators, there we will have a software managed, which is also called explicitly managed storage. So one of them is activation buffer, another is FIFO, another is this. If this raster file anyway, this will anyway store the output, but especially this activation buffer and wait FIFO, they are explicitly managed. Now why? See, CPU is a general purpose. So here we are discussing the characteristic of memory and the characteristic of the computation. This figure is very nice to explain what we are doing. So CPU is a general purpose processor. That means we don't generally know which software, with which of the application we will run on it, right? CPU will run thousands of types of applications. So unless you know the application, right? You can't perfectly say, okay, I will have this data or this data, right? Only when the application runs, that time you know what is the access pattern, and that's why let hardware manage it. On the other extreme is this TPU. TPU and other accelerator, they are like customized. They are designed for a very narrow range of applications. They will only do those applications nicely. They will not do other applications nicely. So now, because they are used for only very small range of applications. For those applications, we can thoroughly optimize it, right? For those applications, so because we have just a very narrow range of applications, most of them are just machine learning or deep learning application. So we can design our architecture in a way that for those applications it is very good. For all other applications it will give near zero performance or very poor performance. But for those applications it will give very good performance. So that's why, because we know the application, we can have this software managed or explicitly managed memories where the programmer can directly write the code that I want this data in this memory. Whereas in CPU, we don't directly write code for storing this data here, this data here. Hardware will manage it. That means you can't, like you might have programmed in C++ or Python. In Python, you never write any code that I want this data to be moved to L1 cache, L2 cache, L3 cache. You don't do that. Right? Whereas in TPU, you can write, I want this data to be moved to activation buffer, or I want this weight to be moved to FIFO. Okay, that is the meaning of explicitly managed. And because GPUs are somewhat general purpose, somewhat for graphics, so that's why it has both. For handling a broad range of general purpose application, it has hardware managed caches. Okay, and for mostly handling to the graphics application and deep learning application, it has this shared memory, which is explicitly managed. Okay, so that is the difference in the memory subsystem architecture. Now, in terms of compute primitive, here, I mean, CPU. In CPU, of course, nowadays CPUs also have vector unit. So in CPU, usually, if you just forget vectorization for now, just for a moment, then in CPU, we are always multiplying one scalar with another scalar. Whereas in GPU, if you forget the tensor code, okay, just for now, forget the tensor code. Then in CPU, we are multiplying, in GPU, we are multiplying one vector with another vector, right? GPU is all about multi-threading. Okay, so we are operating on a var. A var has 32 threads. So all of them are multiplying. All of them are doing the computation. So we are operating at the granularity of a var. That means a vector. Whereas in TPU, as the name suggests, we are operating on matrices. We are directly multiplying two matrices. That is what this systolic array does. Okay, we are multiplying one matrix with another matrix. And now you see why GPU introduced tensor core. Because tensor core can also directly multiply matrices. Okay, tensor core of GPU can directly multiply 4 cross 4 matrices, right? You remember? In tensor core, we can multiply two matrices. Each of them is 4 cross 4. Because in deep learning application, you have to multiply tensors. That means you have to multiply matrices. So why multiply them using vector by vector? Why? It's much better to have a hardware which directly multiplies matrices. And that's why now you can see in CPU, they have already introduced vector capability, right? All the recent CPUs that you will see, they all have vector capability. Plus, some of the most recent CPUs, they also can multiply matrices directly, both from IBM and Intel. Those CPUs can directly multiply matrices. So you can see why those new capabilities are being introduced. Because if you only do scalar multiplication, it is very inefficient. Okay, so I hope you understood what is the broad. We always have to remember the big picture. Okay, what is the why it is that TPU is so efficient? Because first of all, it is directly multiplying tensors, plus it has explicitly managed memories. And because CPU, GPU did not have that fully, so now they are also moving towards that. Okay, now actually not just 3, there are 4 versions of TPU. I have slides for 4th also. I will discuss it later because I want to discuss many accelerators so that you get a very good picture of all the types of accelerators. Of this, TPU version 1 is for inference only. Version 2 and version 3, they are for inference and training both. Okay, so how do you decide this? I will explain and then I will ask you. So first I will discuss version 1. Then we'll discuss version 2 and 3. Okay. So this is how version 1 looks as a PCB. Okay. So now TPU is a weapon. I don't have that figure. There is a very nice figure I have, but I will show you some other time. So TPU is an ASIC. So let us ask some of our EC students. So Anubha or Sagar, do you know what is the difference between a CPU, GPU, ASIC, and FPGA? Let me open that figure. Yeah. Okay, I think it is very good. First, we have to understand this figure, because unless you understand this figure, you will not get a big picture of the whole architecture. So we have hardware here means the programming, the computing system. Now you could have either a general purpose system, or you could have a custom purpose, right? So see, ASIC means application specific IC. IC means integrated circuit, but it is specific to that application. Okay, and opposed to that is general purpose. Okay, so we have now in the general purpose, CPU is the most general purpose, right? You can use CPU for a very broad variety of tasks. Whereas GPU is somewhat general purpose, especially modern GPUs, but at the same time they're not as general purpose as CPU. They are still slightly more inclined towards graphics. That means if you use GPU for scalar, they will not give good performance. Okay, so now GPU. Now in terms of specialized or custom built circuits, we have FPGA and ASIC. Now what is FPGA? FPGA is just a board where you get programmable logic. You have an FPGA board where you can program that logic to do anything. Okay, so and see, suppose you purchase an FPGA today, you use it for suppose video processing. Tomorrow you use it for audio processing. Third day you use it for suppose speech processing. That means it is just programmable. You can always reprogram it. You can always reprogram. That's why it's called field programming. You go to one field, you program it. Go to another field, again program it. So it is not fixed logic. ASIC is fixed logic, but FPGA is not a fixed logic. Okay, FPGA's whole idea, whole benefit of FPGA is it is configurable. Okay, whereas ASIC is just custom built. You have to design ASIC, and that will work only for that purpose. It will not work for any other purpose. Okay, and every ASIC you can't reprogram an ASIC. Okay, ASIC once made, it is made for that. That's all. Okay, it is just a fixed logic. So now you can see, because ASIC is so much custom built, that means it is so much application specific. For that application, it will give very good performance, very good energy efficiency. Whereas for other application, it may not even work. Even if it works, it will give very poor efficiency. Right? Whereas CPU, it will give good, reasonable performance for all of them, but it's like jack of all and master of none. You might have heard of that phrase. It is on average good for everybody, for every application, but it's not specifically good for anything. And now the whole spectrum is there. This is most general purpose, but least specific and least. I mean, it's generally worse in terms of performance. But ASIC, it's highly good for one application, but not good for other applications. So all the accelerator we will discuss in this course, you have to classify in this. But it's mostly very easy. Most of them are ASICs only. Most of the accelerator that you're designing, they will be ASIC, right? Because a company, if they are designing something for deep learning, they will design an ASIC. General, some of them have used FPGA also. And the architecture, right? CPU is latency oriented, GPU is throughput oriented. We have already discussed that. So any questions on this? Any questions? Kunal, any questions?
Sir, why we are putting FPGA in it flashed?
FPGA?
It can use for a multiple purpose. So why?
Yeah, FPGA you can use for multiple purposes. Yes. So what is your question?
So FPGA is not for single purpose, right?
Yeah, FPGA is not. I mean, you purchase an FPGA. Yeah, tomorrow you use it for something else. Third day you use it for something else. Yeah, it is just a logic, programmable logic.
So why not we have categorized this FPGA under general purpose?
It's not under general purpose, it's special purpose. FPGA are classified under special purpose.
So special purpose means we can do only a few things, right?
I mean, no. I mean, it is not general purpose. Like general purpose means any application you should be able to execute on FPGA. It's not like that. When you program it for one thing, it can only do that thing, right? At that time, it will not do any other thing. If just in single program it can do everything, then why it is a need? What is the need of reprogramming?
Sir, can we compare the cost of these devices?
Yes, that's a good question. So actually, see, the whole point is like CPU. See, GPUs are if you ignore the performance, right? Suppose you ignore the performance, then GPUs will be costly than CPU. And FPGA, I think I have that cost in some other presentation. I will show you that cost inside. There is that cost. Let me show you. There's some this. So this is this is GPU based. Okay. So okay, can you see this? So this is for a particular GPU, right? This is not like very generic statement that this is true for all the GPUs. But this, and again, this is DSP. Here we don't have ASIC. DSP is not same as ASIC. Okay, DSP is not same as ASIC. So we have this GPU, which is just embedded GPU. So something like just this much. You can hold it with 2 hands, just this much size. I have it in my lab, in my office. Just this much. That costs $600. Now DSP costs $1,000. FPGA it costs more than $2,000. Now ASIC. Now ASIC is actually something which a company will design. And designing an ASIC means you have to yourself design a full ASIC. Okay. So for example, Google, they will hire somebody to do microarchitecture work, somebody to do RTL work, somebody to do this, somebody to do that. And designing an ASIC is only good if later you will manufacture it in a large quantity. Right? See, CPU design, it will be good for many things. But ASIC, right? You design tomorrow, application changes and your ASIC becomes useless. Right? For example, let's give you one example, like TPU. So TPU, they originally started designing TPU in 2014. Okay, 2014. So until now, it is like maybe 6 or 7 years. They have only 4 versions. Okay, TPU 1, 2, 3, and 4. They have only 4 versions till now. Why? Because designing an ASIC takes a lot of time. Okay, designing an ASIC takes a lot of time. And lot of cost. It's not that every company can design it. Only some of the large companies can design it. Fine. So and that also they will design. So that's why for most of the other companies they have to either use CPU, GPU, or FPGA. Whereas ASIC means it is just for that purpose, and but for others they can't use it. So it takes a lot of initial investment. Later you may sell a lot of chips and you may recover that cost, but initial design takes a lot of effort. Fine. Okay. So we'll.
So
yes.
that means that ASIC design will be designed in a foundry separately for a particular specific design, sir. The chip will be designed in the same way, sir, fabricated for ASIC.
No. See. For example, like I can tell you about TPU. So TPU, like Google's architect sitting in Google's office, they will design the microarchitecture, and they will give it to TSMC or Global Foundries or Samsung or Intel, who will design the actual hardware chip. Most of the design is nowadays I think TSMC is number 1, Taiwan Semiconductor Manufacturing.
Yes.
So they are designing it in 3 nanometer and so on. So that you will do. But now how many of us can even get even one chip fabricated?
Yes. Depending on the requirement of the chips and also they will then accordingly.
Yeah, they will design. Yeah, exactly. Yeah,
that's why it is cost to this.
Yeah, it is very costly. But once if you order it in a bulk quantity, right? Sure. Suppose like 1 million or tens of millions, something like that, whatever. Then you can recover that cost of that R&D you have done.
Yes, yes. That's it gets popular and all, then you can get money out of it.
Yeah.
Then cost can be recovered.
Yeah. But FPGA, you just purchase an FPGA, same
yes,
FPGA
it can be reused and reprogrammed. Yes,
right?
It can be reused and reprogrammed again and again.
Yeah, reprogram, and even if you stop using it, just resell it.
Yes, it can be utilized. Sure.
So let's tell you.
Thank you.
Okay, so let us go on. And but one more thing I want to say is that TPU uses systolic array, and Amazon has also designed one inference chip that is called Inferentia. That also uses systolic array. Okay, I tried to find out whether I can make a PPT, but these companies don't reveal the details. They have just told that they're using systolic array, but more than that, they have not revealed details. So despite searching a lot, I could not make a presentation of that. But this part, they have published a paper. Google has published a paper. So because of that, I know that all the details, internet details. So that's why I made a presentation on Google's paper. But I wanted to also make it clear that there are other designs also which use systolic array, such as Amazon's Inferentia. Okay, so first thing I explained what it means that TPU is an ASIC. Okay, so TPU connects to the CPU over a PCI Express bus. Okay, so remember, just as with GPU we need a host. Similarly, with FPGA we need a host. With ASIC we need a host. So we always need a host. Okay, CPU is always required. Okay, so host sends TPU instructions for it to execute rather than TPU catching them itself. Fine, till now, nothing much. Again, I would not expect you to remember all these details, but at least you should get a broad idea. So whole idea is because CPU, just as CPU to GPU communication is costly, right? Similarly here, CPU to TPU communication is also costly. That's why our goal is that TPU should run most models completely from input to output, maximizing the ratio of TPU compute time to IO time. Okay, now computation is done one layer at a time. See, we have just I'll come back to that point. We have this hardware. Okay, so we will do the computation of one layer, store that output of first layer here, and as you know, output of first layer becomes the input for the next layer. Right? Output of one layer becomes input of the next layer. So, so that's why we overlap execution allowing the matrix multiply unit to hide most non-critical path operations. So whole point is, while we do the computation of first layer, we bring the weights for the next layer, and we store it in the weight FIFO. Okay, so this matrix multiply unit, it is a systolic array. This acts as a systolic array. That's why we have this systolic data setup, because we need that data in a certain pattern. Right? From the previous slide, you remember, we need the data in a certain pattern. That setup is done here. So, and the weights of the neural network, they are originally stored in the DDR DRAM. Okay, we have a DRAM which stores the weights. Okay, and now this is off chip. Okay, this is off chip, and this FIFO is on chip. So we fetch the data from by data I mean the weights. Okay, the weights of the neural network. I fetch it for each layer. I fetch it one at a time. Okay, then so the weight is here, and the first input initially, first layer's input, that will just the input image that will be stored here. That's the activation, right? You remember input activation is same as input feature map, and that is initially stored here, and we will multiply them. Okay, and then our whole the convolution operation is tasked as a matrix multiplication. So you remember now why we discussed that matrix multiplication. How can we can lower a convolution operation into a matrix multiplication operation. Fine. So and that matrix multiplication is performed by this systolic array, and the results are stored here, accumulation result. And then you know that there are other layers also, like value layer, coding layer. So all those operations also happen, activation layer, cooling layer. And now we get the output of the first layer. Output of the first layer will be stored here. That's called unified buffer, local activation storage. And once it is stored, then we can bring the suppose, and then when suppose finally the computation of first layer will finish, then we will fetch the weights of the next layer. So the weights of the next layer will be multiplied with the inputs of this layer. Okay, so that again this systolic array will be used. So our whole idea is that we should keep the matrix multiply unit busy. Okay, because if it is not remaining busy, that means we are not, we will not get good performance. And any questions till this point? The whole idea of computation is very, very simple. Unlike CPU, which has a lot of complexity, here it is very simple. Okay, if you understood, that's fine. It's a very simple operation. Now, there are two things which I wanted to highlight. One is that, see, you try to see how much bandwidth we are getting. Here, we are getting very small bandwidth, right? We are fetching from DRAM. It is only just 30 gigabyte per second. Whereas this transfer is happening internally, that is on chip. This transfer is happening on chip. And here, we are getting that much higher bandwidth. This is because this is on-chip transfer. This is 167 gigabyte per second. And here you can see, this is the host interface, right? So our host, that means CPU will be sitting here. Fine. So host, it will be sitting here. So here you can see that bandwidth between host and TPU is very small, only 14 gigabyte per second. And that's why we want to reduce the communication with the host, because TPU itself can work very, very quick, fast. But your link with the CPU is very, very slow. So your performance will be degraded. Fine. So that's the reason we want to, even for CPU, GPU, or any accelerator, we want to minimize the host to device communication, because that communication is very, very slow. Each of these accelerator can work very, very fast, but if you always start talking to the host, it will become very slow. It's just like that. Suppose this room is very, very big, but only one door, very small door is there. So even though a lot of people are trying to get outside, only one person can get outside in a single cycle. That will slow down your eviction from the room. Okay, so that's the idea. Okay, so TPU uses a weight stationary architecture. What that is, I'm not discussing now. If I later get time, I will explain. There is weight stationary, input stationary, output stationary. So for right now, you can just skip it. So here, weights are preloaded into MAC array, and activations are marching from the activation storage buffer. So what happens, once we fetch the weights, we will store them here. Okay, and there may be multiple inputs that get multiplied with the same weights. For example, there are R, G, and B. There are 3 channels, right? So R means it's R channel, that means red, green, and blue. So red, green, and blue, they will all be multiplied with the same the weights of one layer. So we load the weights first, and then we march the activations. Activation means input. So because weights are already preloaded into MAC array, so weights are read much less frequently than the activations. Okay, that's why bandwidth of activation storage buffer is much higher than that of the weight buffer. So because as you can see, we need activations much more frequently, whereas weights are required much less frequently. Okay, that's why it is okay for us to have lower bandwidth for the weights, but we need higher bandwidth for the activations. So all this you need to design, right? You need to keep in mind, because if you remember the roofline model, if you work only towards the compute, but if you don't, if you ignore the bandwidth, then bandwidth will become a bottleneck, right? And if you only think about very, very high bandwidth, but compute is slow, then compute will become a bottleneck. So that's why we need to think about both. What computation we are doing, which data we need, and if we need the data, with what bandwidth we can get that data. Okay, now let us discuss about the matrix multiply. So matrix multiply unit has a 256 cross 256 max. So in the example we discussed just now, it was 3 cross 3 max, right? That is P, the processing elements. So in the example we discussed, there was just 3 cross 3 P, but here we have 256 cross 256 Ps. Okay, we have a 2D Ps, a 2D array of processing elements, which we are calling MAC units, and we have 256 rows and 256 columns. Okay, and here each of the MAC can only perform operation on 8-bit integer. So that means it cannot support floating point operations. It can work either on signed integer or unsigned integer, but it cannot. That means TPU version 1 has no support for floating point operations. Fine. So now, can you tell me whether TPU version 1 is it good for training or inference? Now you tell me whether it is good for inference or training. Argya?
Sure.
Okay, if you don't know, it's fine. See here, because TPU version 1 supports only integer value weights or integer values, it doesn't support floating point. Whereas in training, we need to operate on floating point numbers. So that's why TPU version 1 cannot be used for training. It can be used only for inference. During inference, it is fine to use only integers. It's good to have floating point, but you can even work with integers. But during training, you cannot work with integers. You will lose all the accuracy. Okay. So as we will see later on, TPU version 2 and 3, they have support for floating point also. That's why they can be used for training and inference both. Okay. Next thing is this matrix multiply unit. It only supports, dense matrix multiplication. So actually, I will discuss that what is sparse matrix multiplication, but I hope you know at least this point that dense matrix multiplication is when you are multiplying two matrices. I think that in last tutorial on Friday, our TA must have discussed, right? What is dense matrix multiplication? What is sparse matrix multiplication? So you know at least a little bit, right? So whole idea is if you're multiplying weights with activations and most of the values are non-zero, then it will be called dense matrix multiplication. Whereas most of the values, if they are zero, it will be called a sparse matrix multiplication. So although you can do sparse matrix multiplication on this matrix multiplier unit, but it is not more efficient than dense matrix multiplication. That means even though the input values are zero, it will still multiply them. Okay, even though input values are zero. See, ideally, if none of the input is zero, we should not do that computation, right? If one of the input value is zero, you should not do that computation. But here, TP will still do that computation. That means it is not intelligent enough. Okay, because it is not intelligent enough, it will still do that computation. So that's why it is not specially efficient. Now, so once you multiply 8-bit values, you will get 16-bit products. These are collected in 32-bit accumulators. So here we have these accumulators, right? So they will collect the outputs because we are multiplying weight with activations, and we are adding many of them. Right, 256 of them we are adding, and we will accumulate them in the accumulators. Now, weights for the matrix unit, they are staged through a non-chip weight FIFO. Okay, so that means see, always systolic array requires some kind of staging or data setup. Okay, because we have that alignment in time, right? It's first input will come first, then two inputs will come, then three inputs will come, and so on. So that staging happens in the weight FIFO. So it reads weight from a DRAM, which is off chip, and that is called weight memory. This is the weight memory. Inference, during the inference, weights are read only because weights don't change in the inference. Weights are decided during the training. The whole training is about deciding the weights. Okay, and intermediate results are held in the 24 megabyte on-chip unified buffer. So that is the unified buffer here. That means intermediate output. Whatever output we get from first layer, that will be called intermediate output of the first layer, which will become input of the next layer. So intermediate results, they are held in the 24 megabyte on-chip unified buffer. And right now storing the output, it will become input in the next layer. So that's why it will serve as an input to the matrix unit. Okay, so this is just a floor plan. This is not actual chip diagram. This is just a, it's called a floor plan. So how much storage we have? Try to count. Here we have 24 megabyte of storage. Here we have 4 megabytes. So how much total storage we have? How much total storage we have on chip? Sagar?
Yes, sir.
How much total storage we have here?
Sir, 28.
Yes, yeah, very simple. Yeah, it's not a tricky question. We have 24 plus 4, total of 28. And one more thing is the control takes only 2% of the chip area. Okay, this is really, really good. TPU spends only 2% of overall chip space for the control logic. So whereas in CPU, you have a huge portion of the area dedicated to control, and you have very little area for the compute. because it has CPUs have very complex structures like out of order and so on. I mean, I will later discuss very briefly, but if you try to get into deep, you will probably drop the course. So they are so complex topics. Of course, this is a compulsory core course, so hopefully you will not drop it. But yeah, I mean, those CPU, those structures become very complex. Even in my UG course, I don't discuss them. But here, the whole idea is try to keep the chip simple. Okay, that was the whole design philosophy. And DRAM ports take some, and PCI interface that takes some. Host interface takes some. So okay, so now you can see and unified buffer, which is stored for activations, that takes 29% of the chip area, and matrix multiply unit that takes 24% of chip area. Okay, so this is the main computation workhorse, right? This is the actual horse which is doing the computation. So that has been given 1/4 of the chip area. Fine. So let us go on. Now as for the ISA, it has SISC ISA. So you can actually read about RISC and SISC. So there are two broad ISAs. One is called RISC, another is called SISC. So can anybody tell me what is x86? Which of these two categories does x86 fall in? Have you heard of these terms, SISC and RISC?
x86 is SISC.
SISC, very good, yeah. And what about ARM? What about ARM?
This is that reduced instruction set array, sir.
Yes. That is reduced versus complex. Yeah.
In one cycle.
So ARM is what?
RISC.
Yeah, Krishnan knows. Yeah, he has some practical experience. Okay, very good. Yeah, I will discuss more about RISC and SISC. I have that presentation. I will show the presentations. So the whole point is in SISC. So even if you could not understand, wait, I will explain. Let me first explain that. I should maybe put that in there. Yeah. Okay, so we have two broad categories of RISC. This RISC and SISC, they are not ISAs themselves. They are category of ISA. Okay, in RISC, it implements simple instructions that have a simple regular structure. And number of instructions is typically small. Okay, example like ARM ISA, which is the most popular ISA. IBM, PowerPC, HP is PRISC. So now these are not very known, but ARM is the most popular ISA. Okay. Whereas in a SISC, it implements complex instruction sets that are highly irregular, take multiple operands, and implement complex functionalities. That means in SISC, you will have very few instructions, but they can do a lot of things. Okay. For example, in SISC, you may have one straightforward instruction for doing a sine, or cosine, or tan theta. Whereas RISC will never have it. In RISC, you will have to compute sin theta, cos theta, tan theta using maybe Taylor series expansion or some other, in a software. And number of instructions is large. Of course, in TPU, number of instructions is just 12. Although TPU uses SISC, but TPU does not have a lot of instructions because TPU is for custom purpose. So you know that I will only do very few things. I don't need thousands of types of things. I will only do very few types of things. That's why in TPU, although it is SISC, it has very few instructions, just 12. And number of instructions large. So x86 falls under SISC. So, okay, coming back here. So here, the benefit of using SISC in TPU is that because instructions are sent over PCI Express bus by the host, you don't want to send a lot of data over PCI Express bus. Okay, so you keep you send only few instructions. Okay, and those instructions itself will do a lot of things. So you don't want that PCI Express bus to become a bottleneck. An average CPI of instructions is between 10 to 20. That means each instruction, CPI means cycle per instruction. So each instruction takes between 10 to 20 cycles. Here is some example instructions. You don't have to memorize it. They are self-explanatory. And now coming to software. So I'm sure you will run. You either you already know about TensorFlow or you will learn a quick introduction to it in some course. So you also have to see what is the programmability. See, many researchers, when they write their paper, they design an accelerator, but you can't use them easily because they only propose a new hardware without any software support. That's what happens especially when you try these embedded boards like Raspberry Pi or something like that. You don't get good software support. Something which runs very easily on a normal server GPU, it fails to run on that embedded board because of the lack of software. So the first requirement for a good accelerator is that at least it should be usable through the software interface. So here, TPU can support TensorFlow programs. Okay, what are the other ideas? Design philosophy: to get high performance, we should keep the matrix unit busy. If matrix unit remains idle, you don't get much performance. Okay. So again, now matrix units uses systolic execution. I have already discussed that to save energy by reducing reads and write. So how does systolic execution reduces energy of reads and writes? Anybody can explain me? What is the whole? How come systolic array is reducing the reads and writes? Bhanu? Or anybody can please speak. That was the first slide of the systolic array lecture that I presented today. How come systolic array is saving the? Yes, anybody?
Sir,
Because
Gaurav, yeah, Gaurav.
so because here parallelism is working, sir, and all the time they are not asking for the data from the memory. It is already in that slot.
Yeah, very
So
close.
again,
I need
they're
a
not.
little bit more precise. Yeah, you're always there, already there, but almost there, but little bit more precise. Yes, Sagar.
sir, all the time we are not accessing data from memory.
Yeah, that is a more precise answer. Yeah.
Yeah.
We are reducing the memory accesses. Only one P accesses from the memory. Other P's get the data from the nearby P. All of them are not sending requests to the main memory. That means data movements are local across the P's. Okay, so here you can see each of the P. Here, see here we have this matrix multiply unit. Now suppose this is one mat. It is not directly getting data from D. It is getting the data which was received by the previous P. It's just this P. That's the idea. Now, systolic arrays are heavily pipelined. So if you know pipelining, you will understand it. If you don't know, that's fine. It's like a two-dimensional. Systolic array is like a two-dimensional pipeline. It's not exactly pipeline. Systolic array is not exactly same as pipelining, but there are some similarity. Now, another thing is, it takes 2n minus 1 cycles to read all elements of the product of 2 n cross n matrices. So let us see that in that presentation. I'll get to show that. This, yeah, here. So okay, so here we have n equals to 3. Okay, so what is value of 2 minus 1 is 5. Right, 5. So now let us try to see here how it takes 5 cycles. So to get so first output becomes ready at cycle number 3. Okay, and last output becomes ready in cycle number 7. So 3, 4, 5, 6, 7. So 5 cycles it has taken for us to read all elements of the product of 2 n cross n matrices. So here the whole idea is each P will not directly give the output also. It will only give the output to the next P. Okay, so only one by one it will move. So all the movements are local. It's not like very far movement. So Okay, so it takes so much cycles to read, but of course, total computation takes more than 2n minus 1. I will, you can think, but just the reading of the, how much cycles it takes to produce the outputs, that is 2 minus 1. From the first output being generated to the last output being generated. So that's why latency of matrix multiplication depends on the matrix dimension, which is not good if you need constant latency. If you need the output in the constant latency. Now here is the quick summary of the systolic data. Here we have wait memory. Here we have activation memory. So here you can see the data is staged like this. The wait memory has the data. Now activations, they flow this side. Waits, they are reloaded. Okay, we fetch in the we fetch that in the wait FIFO and then we preload them. So each MAC already has the weights stored in it. And partial sums are generated, they keep on going down. Okay, and finally, these are the accumulators. So we will accumulate all the sums. Fine. So we'll